So talk about problems and then the algorithms that solve those problems. So let's say we had a problem like we want to go from where we are right now, from the Jersey Shore to New York City. How would you do this? This is a problem. A problem is something you need to get, let's say, from point A to point B. And there may be many ways to solve the problem. But if this was the problem and I asked you how to solve it, what would you say?
To drive, take a train.
Okay. And if you wanted to drive, how would you drive? Just, off the top of your head.
18 north to 9 to
Okay. Anyone have a better idea?
Parkway.
I'm not saying this.
Parkway North to exit exit 126, and then get on Turnpike to exit 114.
Okay.
114 to Lincoln.
So already we have two algorithms, right? To solve this problem, right? What about this algorithm? Drive your car from the Jersey Shore to Miami. Drive from Miami to Los Angeles to San Francisco, and then from San Francisco. That's a third choice. So now we have three algorithms. What do you think of this one?
Not efficient.
Not efficient. Does it work?
Yeah.
Will this algorithm solve the problem? Yes.
Mhm.
Is this a good algorithm to use? Is it the best way? Gas, tolls, miles, So actually, one of you said take Route 9, right? And one said take the Parkway. The Parkway is faster but has tolls, right? So you can kind of get into a debate, what's the better algorithm? Right? And all these algorithms work, but you wouldn't want to use this one because it's inefficient. How would you make the argument that this is not efficient? Probably using time, gas, wear and tear of the car.
Any one of the variables that,
There's a lot of ways we could measure what's a good algorithm and a bad algorithm for traveling. And I guess it would be like time, gas, tolls, hotel bills, and all that kind of stuff. So, suppose you wanted to go from Jersey to San Francisco. It's a different problem. Some of the choices could be to walk, drive the whole way, go to an airport, fly, then rent a car when you get there. So now you have lots of sub-steps to your algorithm. And you start to get into the question of like, is an airplane faster than a car? Well, it is, but if you wanted to go from here to New York, you wouldn't take an airplane. Because you'd have to go to the airport. There's too much overhead in going to the airport than flying there and renting a car. It's too short of a problem to use that technique. But if we know all these techniques, like walking, riding a bicycle, driving a car, flying an airplane, if we know all of these and use them wisely, we could put together the algorithm that's the most efficient to go from anywhere to anywhere. Right? So you wouldn't want to walk to San Francisco, right? That wouldn't work too well, and you wouldn't want to fly an airplane if you're going from here to New York. Too much overhead to use that efficient way of travel. Something like this is going to come up. Well, first of all, these are real data structures questions. I'm not just coming up with these to make a point. If you go to like MapQuest and you say I'm here and I'm going to there, and they find you the best algorithm, they actually use data structures to find you the best algorithm. But this just kind of gets across the point that we can have many algorithms to solve a problem, and some of the algorithms are a lot more efficient than others, so we would assume let's take the most efficient one. The other thing we'd like to do is when we're throwing out all these ideas of how to get to where we're going, it would be nice if we can not only come up with what we think is the most efficient algorithm, but maybe we could prove it is the most efficient algorithm. Nobody will ever come up with a better one. And then we can be comfortable knowing this is the shortest way, the most efficient way to solve the problem. Okay. Suppose you wanted to go from the room we're in right now over to the gym. Right? You want to go from this classroom over to the gym. would you take a car or take a plane or walk? The car might work if we have, if your car's out in the parking lot, right by the building, and you drove around to the gym, but it even might not be worth it. Might be worth it to just walk, right? So if you're going from the Jersey Shore to San Francisco, walking's a bad idea. If you're going from here to the gym, walking becomes a good idea. Because a lot of times, all these little pieces we're gonna put together have some overhead when you go to use it. Just like taking an airplane has the overhead of going to the airport and waiting an hour to go through the scanners and all that. But if you're going someplace that's across the country, it might be a good idea. So then if planes are faster than cars, should we always travel by using a plane? Depends where we're going.
So, for example, you're saying like walking doesn't scale. In other words, it doesn't
Right.
apply well across the,
Right.
as you
And we're
change the distance.
Right, and we're gonna go over more simpler problems in a little while. Let's say like taking a group of numbers and sorting them. If you have 10,000 numbers, you might use an airplane. And if you only have 5 numbers, it might not make sense to use an airplane. You'd use something that seems less efficient, but for 5 numbers works well. So there's gonna be points where, depending on the problem we're solving, we'll determine which of all the tools we're gonna learn, which ones we use. And we might actually take some of the tools, like I said, if you want to go from New Jersey to San Francisco, you would drive to the nearest airport, then fly out, and then drive to your location. You'd start taking bits and pieces of stuff we've learned. Okay, so suppose we have, like I said, the problems we just talked about are actual computer science problems that use data structures and algorithms to solve them. But this might be a simpler problem. So the way we're going to describe problems is we're going to give an instance, which is basically the input data for the problem. And then we're going to state what the problem is. So suppose we have a collection of numbers, and I kind of left this vague. I'm not saying an array of numbers, but it would help if it was an array. I'm just saying a collection of numbers come in as input. And the problem is, print out the largest number of all the numbers. Okay. How would you solve this problem? Again, just like, when we want to drive from New Jersey to New York, going out to Los Angeles and up to San Francisco and back, it works, but it's not the greatest idea. You could come up with algorithms that are not the most efficient, and then maybe we'll try to get better ones. But is there anything you could think of right now? If you had a bunch of numbers, and you wanted to print out the largest one?
Yeah. Insertion short into an array and then print the last number. Put it in ascending order.
Okay.
You start with
Anyone? Okay. So basically you said step 1. So already you're using, just like the last example, using cars, airplanes, you're using a tool called insertion sort. So what it's basically saying to do is to take all the numbers, which come in disorganized, sort them all from smallest to highest, and then print out the last number. Will that work? Yeah, because you have them lined up shortest to longest, and then you're printing out the last one. Now, does anyone have any comment, now that we're thinking about efficiency? Did he do too much work? Yeah?
what, I thought you were looking for an alternate way that maybe
Okay.
less.
Okay. Yeah, what's
No,
that?
no, but you start with the first one. Instead of going through a whole sort, if all you want is the maximum number, you start with the first and just keep comparing it going down the list. And you have a temp location that basically says, okay, this is the largest of this comparison. And as you walk down, you haven't sorted anything, but you've always kept the highest or the max,
Okay.
the largest.
Okay, so.
And then
now-
print it.
Now we have two algorithms.
Right.
Just like before, we were trying to get from Jersey Shore to New York, and we had a bunch of ways to go, and then someone says, my way's better than your way. That method works. Sort all the numbers, print out the last one. Sort them from smallest to highest, and then print out the last one. Your method says, read the numbers. Don't move them around, just read them. And you said have an additional number called, let's say max.
10 or max.
Max. So you read the first number, store it into max, and then say, is the second one bigger than max?
Right.
If so,
Replay.
then replace max with the new
Right, and then
max.
keep
And just
walking
do
down.
that for every number, and then at the end, your max number
Print
will,
it.
and print out that one.
That's.
Okay, so that's two algorithms. Now, if we're driving from the Jersey Shore to New York, we can use mileage and tolls to figure out which one's better. Can you make an argument one of those algorithms is better than the other?
It depends what's important to you. Let's say time versus memory, et cetera, things like that, I would imagine.
Right, so you're using one extra memory location
Well,
for your 10.
well, if you're going to sort, I don't know what the sort would take.
He said use insertion sort. That's an algorithm we're gonna talk about.
Okay,
Actually,
so I
we'll
don't
talk
know
about
that.
Okay,
I
that one
just
doesn't
don't
take
know.
up any extra no,
Memory.
that one needs a temp space. That'll use up one additional memory spot. Okay.
I mean,
There are sorting algorithms that don't.
Right.
So, if you wanted to make the argument.
Which is faster, I guess, comes down to, is the next.
Okay, well, for sorting to be faster than your algorithm,
I was betting this was faster, I may be wrong on
okay, does anyone, if you had to guess, which is faster? Sort all the numbers and then print out the last one, or read all the numbers and keep track of what the biggest one is and then print that out? Do you have like a gut feeling of one being better than the other?
I feel like just reading it would be.
Yeah, and what would be like the argument?
Because I feel like having to move.
that. I don't have to move things around. I
Yeah.
don't do as many replacements. In other words, if I get lucky on the average, one way I have to always, I have to move things to sort it, assuming
Right.
they're unordered to begin with randomly. The other way, I'm looking and I'm saying to myself, if I get lucky and the first one is max, and nothing else is higher, I never have to change anything.
Wait, could,
If
this
the
is gonna
first
be an
number
inter-
is the highest.
This is gonna be an interesting question. If the first number is the highest, you're done?
No, I'm gonna still have to do a comparison.
Oh, I see what you mean.
But no
Okay.
store.
But you won't have to do any swapping. So if you
Exactly.
get lucky, and if they were, the unluckiest case, the worst case scenario would
Right,
be if
that-
you started, if they were smallest to highest, you'd be swapping every time.
Right.
That's your worst case.
Right.
And
So-
on
so in
average,
the
you'll
middle.
probably be
Right.
swapping half the time or something
Right,
like
that's
that.
what I was thinking.
I mean, he has to put it in something, like an array, so, and he's gonna have to transverse through the whole array.
Right, he has to read the whole
He's-
array.
Yeah,
To read
and mine, you have to transverse it, well, no, you could just sort it and then take out the last number,
I
still.
read.
Right, so really what it's coming down to is what's more work,
'Cause no matter what, he has to
reading them.
transverse.
or sorting them will take time. Actually, we'll, in the next class, we'll go over insertion sort, because that's how much time that one takes. But the argument would go we're not ready to make the argument one algorithm is better than the other, but your algorithm, which reads the numbers, will take a guaranteed, if you have n numbers, you're gonna take at least 10 steps. And at each of those steps, some percentage of the time you have to do a swap and sometimes you don't.
And I'm assuming it's gonna scale linearly. Bigger.
Right.
Just smooth right up.
Right, so let's say for 1,000 numbers, your algorithm might take somewhere between 1,000 and 2,000 steps, maybe 1,500.
Right. Okay.
Do you remember what insertion sort's running time is in, even though we'll talk about that next class, but it's something, well, the idea is this, if you have 1,000 numbers, how many steps will it take? And it ends up being, we don't need to talk about this tonight, it ends up being something like 1,000 squared, which would be 6 zeros, 100,000 steps, approximately 100,000 steps, where your algorithm might take 1,500 steps. So, and for really small numbers, it might not even matter. You know, it'd be like, you don't wanna take an airplane if you go into the gym.
Right.
For small numbers, his might turn out better than yours, but for large numbers, your algorithm might be better. Is there a way, now that you came up with that suggestion, is there a way to argue, so your algorithm takes if there's n numbers, you're going to take approximately n to 2 times n, somewhere in there.
That's the most I can,
Right. Is there any way somebody could ever come up with an algorithm that could declare the maximum number without even looking at all n numbers? Like just ignore some of the numbers and say, yeah, this is,
there may be, but I can't think of it.
well, anyone want to make an argument it can't be done? That you, the only way you'll ever be able to declare this is the largest number, you have to at least look at everything.
I can't, otherwise it becomes a probability problem to me, I mean, because you're guessing. Because what is my criteria for saying skip it?
Right. If
I
you
don't
never
have
looked
one.
at it, how can you skip it?
Right.
Now, the thing.
Now if they, go ahead.
If later on, if I told you the algorithm, the numbers were already sorted in the first place, then you could look at one in the middle and say, skip this
Oh,
head.
yeah, then I
Right,
could
then
jump.
you can start
I
skipping.
can start dividing in a binary kind of
Right,
way.
and this is something we'll come up, this
Yeah,
is
oh,
something
that-
we'll
that-
use later on.
I'm assuming I have no a priori information.
Right, okay. So you could kind of make an argument that all algorithms that anyone would ever come up with, at a minimum, require that you at least look at all the numbers. So every algorithm in the world, will it take at least, for 1,000 numbers, will take at least 1,000 steps, minimum. And your algorithm takes 1,000 to 2,000, which we could kind of make an informal argument, your algorithm really can't be made better. Because every algorithm requires that you at least look at the numbers. So we want to come up with a way of saying, just like when we're traveling from the Jersey Shore to New York, we might say time or gas or as our mechanism to say one's better than the other. We need to come up with a way to say one algorithm is better than the other. And it's going to be related to the number of inputs.
And I was looking at the way you laid it out, I didn't know the size of the list, so in my mind, I'm saying, hey, if it's a small list or it's an enormous list, what's the fastest way to do it?
Right, but here's the thing, so there are gonna be questions where we're gonna say, well, if the number of inputs is between 0 and 6, one algorithm is better. Between 6 and 25, algorithm 2 is better. Above 200, from 200 off to infinity, some other algorithm is better. And the one we're always going to say is the best is the one from 200 on to infinity. We'll just say, that's the way we're gonna make our argument. We're going to say the best way to solve something is if the number of inputs is really large. It's a vague concept, but we're gonna say if it gets really large, then this is the best algorithm. But we'll always be mindful of the fact that if you have really small inputs, there might be a better algorithm. Just like going from here to the gym, you wouldn't take an airplane because that's a really small trip. But in general, if you're going on a really long trip, airplane's the best answer. Right? So we're going to use an argument, something like that. So the way we're going to argue if an algorithm is good or not is by saying if n was really large, this is the best algorithm. We want to, going down the road, we're going to make that argument. So we'll formalize that in a little while. Okay, so now here's a suggestion. I always like to suggest a crazy algorithm, just like driving to San Francisco to get to New York. Here's the algorithm. Step 1, sort the numbers. Step 2, print out the highest number. That was your algorithm. But I want to do a crazy sorting algorithm. So here's the analysis of this algorithm. Well, it's how much time does step 1 take, and then how much time does step 2 take, and add them together. Like if you're going, driving to the airport and then flying on a plane and then renting a car, you have to add 3 pieces together. So the question is, how do we do the sort? How long will that take? The last part where we just print out one number, that takes a constant amount of time, however long your computer takes to print out a number. So this is the step that starts to become, it's a sub-step of our algorithm, and that's the one that, depending on how we choose to do it, will matter. So suppose we did this. Suppose I decided, here's how I'm going to sort the numbers. I'm going to take all the numbers, and I'm just going to calculate every permutation of them. Just line them up in every possible order. And then, once I line them up, I'm going to go read them all to make sure each one gets bigger after the one next to it, as a check, to check that they're sorted. If that doesn't work, I try another permutation, check it again. And I do this until I'm finally done. this is an unbelievably bad sorting algorithm, right? Because if we had, what's that? It's a terrible sorting algorithm, but it will work. Just like driving to LA and San Francisco will get you to New York, but it's a terrible way to go. If we had 20 numbers, okay, so how many permutations are there? It's n factorial, if you remember that from probability class. If n was 20, 20 times 19 times 18 times 17 equals 2.43 times 10 raised to the 18th power. If we had a processor that could execute one instruction, one gig of instructions per second, and let's say we could compute the whole permutation in one instruction, which you can't do. We would take at least 20 instructions just to get the permutation run, another 20 instructions to check that it's right. But if we could do that on a 1 gig processor, which, if you go to Staples now, how fast are the processors? If you buy a run-of-the-mill computer, are they more than 1 gig?
Like 2.
You can get 2 gig processors? Okay, so then it would be half this time. The algorithm, this algorithm for sorting 20 numbers would take 76 years to run. It would run, but it, you'll be dead by the time. So it's what good is it? Right. And if you had a 2 gig processor, it'll be done in 35 years, but if I made n 21, it'll take 21 times 35 years. So just for a pretty small n, like 20 or 20, it's not even worth it to run this algorithm, but this algorithm works. So this algorithm would solve the problem, but it's very inefficient to solve it this way. So then we want to look for a better algorithm. And then okay, so the topics. So at this point I was saying, does anyone have their own suggestions? So we already have some good suggestions. And then the idea was the concept of the best possible algorithm. So the best possible algorithm, and we'll get to this like in a class or two, we'll make a little more of a formal argument, and every algorithm would take at least n steps before we can declare something as the maximum value. We have to at least look at the number before we can say it's a maximum value. If they were pre-sorted or quasi-sorted, we might be able to look at one and then say these 3 I don't have to look at, but we don't have that situation right now. We want to look for stuff like that. But right now, there's a concept of completeness. And completeness is when you make the argument, my algorithm's time can't be beaten by another algorithm. So if you came up with an algorithm that took, let's say n was 1,000, if you came up with an algorithm that took n steps, and every algorithm in the world must take a minimum of n steps, then yours is tied for the fastest there is. There's really no point in coming up with a better algorithm because there really isn't a better one. And that's kind of the argument we want to make. Okay. Okay, so this is the problem you were talking about. I think this is the one you're talking about, right? The Skyline silhouette? Okay. So, here's a question that we'll use. I mean, this would be, if you've never seen this before, well, okay. I'm trying to think, well, if you've never seen this before, this might seem like a tough question. But an answer for this question could involve find max and sorting, the 2 things I've talked about in the past. But here's how the question works. We have a collection of rectangles, which we'll call buildings, their heights and widths, and the problem is to print out the Skyline silhouette. So it would look like this. Let's say our input for the problem was building 1, the left point of the building is at 3, the right point is at 4, and the height, the right point is at 7, and the height is at 4. That's this building right. So here's our skyline. We're looking at our skyline. And we have this building that has a height of 4, and it goes from 3 to 7. So we know its starting point, its ending point, and its height. Is that the way the problem you've sorted before? Okay. And then we can have, the city can have as many buildings as it has, but it's some finite number of buildings, can't have infinitely many buildings. The buildings can overlap. So for example, we have our second building, starts at 11, ends at 20, and has a height of 8. So that building looks like this. From this point of view, remember from a different point of view it would have looked totally different. From this point of view, the third building starts at 15, goes to 29, and has a height of 3. Now, if, let's say, it's dark out, so we can't really see we can't tell if this building is in front of this building, it doesn't really matter to us. We only see a building or no building. We can't really tell which one's in front of the other. And our goal, if this was our input, and we could have many, many buildings, I just gave 3 as an example here. We want to print out as the answer what the skyline looks like, which is basically if I got rid of this part, where the buildings overlap. So does it make sense what the question is? The input is a bunch of buildings. And we're not going to solve this one tonight, like programming-wise, but just we'll throw some ideas around how we would do this. But sorting and using the find max algorithm would help. Okay, but just first we want to understand what the question is. So we have a finite number of buildings, so there's n buildings. The more buildings, the more work your algorithm is going to do. And the buildings could overlap each other, and we want to print out just the outside of the highest building at any point. We don't want to print out the parts of the buildings that overlap. So the output would be, so last semester you had to actually print the buildings. You couldn't just print out these numbers? Okay. So it's a lot easier.
I'm pretty sure we had to join.
Okay. But anyway, so the answer would be starting at 3, 0, then going to 3, 4. So basically, the way the output should be here is just put this point, 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 then this point, and then this point. So this is kind of, see how this could be considered the silhouette of the skyline? So now the question is, if you were given buildings as input and wanted to print out the silhouette of the building, of the skyline, anyone have any ideas? If you haven't heard this problem before, this one takes a little thinking. But, well, first of all, if the buildings couldn't overlap, it would be a pretty easy question, right?
Mm-hmm.
You would read the first building and you'd print it out. Then you would read the second building and print it out, read the third. As long as they don't overlap, it's a pretty, just read a building, print it out. The problem is they start overlapping.
I mean, if I know I'm going to print, well, what I need is the ceiling height. And once I know, and I need the coordinate of the beginning of the ceiling and the end of the ceiling of the first building, let's say, assuming there's no overlapping right now.
Assuming no overlapping.
And then I know that I'm going, for every line underneath that roof, I'm going to print a dot. Or I'm going to print a star. In other words, if I know the width.
Well, wait, hold on. So the question you had to answer is much harder when you have to print all these dots. That's like an extra step. All I'm saying is print this dot, right? 3, 0, this dot, this dot, this dot, and this dot. I know dropping these dots now, that adds a lot of work to it, which doesn't really have anything to do with data structure.
I think of the printer as sort of, I have to print the top first, right? I have to find the highest one. And if I know the highest one, I come down, I gotta know where my baseline is to stop on each vertical.
Right, so here's kind of some of
And where
the...
they overlap, I change the baseline.
Right, so what you're saying, as we're starting to solve the problem, we're saying at any point, are you going left to right as you're answering? Okay. Okay, you don't have to, but that's a good way to do it.
I was
You're going
doing it.
from left to right. You want to know which buildings are more left.
I
than
want
others.
to, I also want to know where there's an overlap. Because I'm going to change my baseline.
You're going to change the height. Whenever there's an overlap, the question you're going to ask, find max. You're going to say, out of all the buildings that are alive at the moment, which one is the tallest? That's the only one you care about, is which one is the
That's
tallest.
where I have
out
to
of-
start.
Right, if there are 6 little buildings under
Right.
here, you don't care. All you care about, out of all the buildings, at any point in time, which
I
one's the
start at
max?
the top and I'm coming down.
Okay, so
And I-
you're doing something like, first of all, the buildings coming in do not necessarily, I'm not guaranteeing the input is from left to right. They could be, I could give you this building first, this
Right.
building, okay, so what's the first step you have to do? Because you wanna go from left to right. I'm giving you stuff in random order, you need them in a particular order. What do
gotta
you do?
sort 'em.
You gotta sort 'em. You sort the buildings from left to right.
Right, and I'm going to sort them from left to right, and then I'm going to look for the highest. So I'm going to look for that high Y coordinate.
Highest out of what?
Out of the buildings that I've sorted left to right, I want to know which one, out of those
Okay.
points, I want to know which is the highest coordinate.
Well, okay, let's say you're at coordinate 3.
Mhm.
The highest building up is 8.
Right,
Do
so
you care about 8 at this point? Do you want to print the skyline up here?
Well, the way I was going to do it, I was going to start at the top and just work my way down, always on each line coming back and forth. In other words, I know.
Oh, that's a different algorithm, okay.
Right,
This-
I'm going left
What you're
to right.
doing is this, okay, this is your algorithm, I think. You want to sort the buildings tallest to shortest.
Yes, and
Then print out the roof of the tallest one.
yes,
Then,
yes, left to right, the tallest one, and I'm gonna come along, and all I have to know is between 11 and 20, is there another building, you know, is there an X coordinate somewhere that falls between 11 and 20 in my mind? Because if it is, that's my new baseline. I have to have a baseline. I'm only gonna print those stars down.
you have.
Till I get to a new
Okay, so
baseline.
somehow.
I wanna know where to stop printing that building.
Well, wait a minute, you're gonna start,
No, no.
you're basically printing roofs of buildings.
Start.
From the highest to the lowest, and then somehow filling in.
Well, but under each edge, each vertical edge, I have to know if there's a roof that intersects somewhere as I'm coming down.
Right, because as you're coming down here at a certain point. this
Instead of
one's
printing down to 0, y equals 0, I've got to stop ahead of time.
on. Okay. How would you know to stop?
That's where I'm going to, that's why I said between 15 and 29. In other words, I'm sorry, between 11 and 20, is there another roof? In other words, is there an X coordinate, which there is, 15, is
Right.
between 11 and 20.
Right.
Whatever the Y coordinate of
This one.
15 is, the high Y coordinate.
Right.
Which would be the right side. That's where my baseline stops, I don't come all the way down then.
Okay, so as you're coming down, you know to stop here because.
Right.
Okay, that might be tough to keep track of. But the other, I think you started an algorithm like this, where you go from left to right, and what you do is you say, you're walking from 0 to the end of the skyline, and you're saying, you sort the buildings from the one with the, whose left wall is the most left, to the end. And then you read the first building, and you kind of throw that into some kind of data structure that says, I now have a collection of one building. And then I ask myself, out of all the buildings in this collection, and there's only
Is
one,
there any overlap?
ask yourself, which is the tallest one? All you care about at any point in time is what's the tallest building at that point.
And the other piece of information I was looking for, is there any one that overlaps this? You know, it's one other piece of information I was looking for.
Okay, but this one,
If it's the tallest, then you don't have to worry about that.
right, so one algorithm, there are several algorithms for this. But one algorithm would be sort the buildings from left to right, then have some kind of data structure that we could throw buildings in, which may collect more than one, may have several buildings. But this data structure has to answer the question, which one is the tallest at the moment? And that's the find max algorithm. Or maybe we'll even come up with something better later on down the road. So now we have one building and we say the maximum height of all the buildings is 4. So we start printing 4, 4, 4, 4. Then that building ends. So it leaves our data structure and we do find max again. And if you do find max with no buildings, you get 0. So now we're printing 0, 0, 0, 0. Now we have a new building come in whose height is 8. So now we're printing 8, 8, 8. Now a new building comes in, which height is 4. So in this data structure, which is kind of vague tonight, this data structure has 2 buildings, and we ask the question, which one is the highest? And it keeps telling us 8, 8, 8, 8, 8, 8. No new buildings have joined our list. Then this building ends. So it pops out of our data structure. We still have all the other buildings that happen to be there at the moment. And we say now, what's the tallest building out of all the buildings? And it says 4. And then we go 4, 4, 4. And as buildings add and subtract, every time a building is either added or subtracted, we have to re-ask ourselves, what's the tallest building? And then just keep printing it. And then if another building adds or subtracts, that may throw off the tallest building one, so we run find max again. That's there's a number of algorithms. Another one.
As you printed across the top of the highest building, and you got to the farthest right edge.
Over here?
Yes. What
Right
happened?
now, at this point in time,
Right.
all the buildings, we could have 8 buildings right now that are all overlapping. We could have a long building here, a short one here. Out of all the buildings, all we care about is the tallest one.
Right.
As soon as the tallest one leaves, we're gonna have a new max.
When the tallest building leaves, what have we printed? Just the dots across the top?
Right. We keep
Okay.
printing the dots along the top.
Only the top.
Only the top, that's all we care
We're
about.
not coming down yet.
No. Now, if a building ends, if a building leaves our collection of buildings we're currently looking at, it's possible that the one that left is the tallest one, so we have to run find max again to see if it's now a shorter building is the new max. If so, then we draw dots coming down to the new height. To the new height.
That's your new.
If a new building gets added, let's say as we're moving from left to right, a new building gets added, that might now be the new tallest building. Maybe not, maybe it will, but we have to check. So we're keeping a collection from left to right of all the, we'll call them active buildings. And we need something that tells us the maximum of them all. And we just keep printing it until there's a reason to stop. And there are 2 reasons to stop is a building has ended or a new building has started. So that's one way to do it. And another way to do it would be if these were integers and not floats, we can actually have an array. We can create an array from 1 to 29 called heights. Initialize them all to 0. Then read any random building. Let's say this building. And we say if 0 is less than 4, then replace it with 4, 4, 4, 4, 4, 4, 4, 4. Then we read this building. And this says 0 is less than 8, so we make this 8, 8, 8. This 4 becomes an 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 8. This 4 stays a 4. So we have 8, 8, 8, 8, 8, 8, 4, 4, 4, 4, 4. And then this one, I'm sorry, 3. These were 3s. And then we read this building, and these are all zeros, so we say 4 is greater than 0. We make this 4, 4, 4, 4. Right, all we're doing is keeping an array of the height of the skyline. And then when we're finally done, each building we read, we just say, does this building make the skyline bigger at that point? And record it. And then we go through and we print out 4, 4, 4, 4, 0, 0, 8, 8, 8, 8, 8, 8, 8, 8, 3, 3, 3, 3, 3, 0, 0. That only works if it's integers. Right, because what we're doing is we're taking each one of these locations and assigning it to an integer. If we wanted reals, like these buildings could be 11 and a half, and the last algorithm would work. Because it's just going from left to right at any point in time. Any point in time a building comes in, we can just start printing the new group. We could do 11 and a half and 11 and 3/4. The integer problem has a more efficient algorithm, but if you have real numbers, you have to use a different algorithm with a different data structure. So this is just like a little flavor of how we can take problems. Oh, this was the hint for what we've just been talking about. So sort the buildings in a particular order, move the buildings from one data structure to another, and have the data structure have something that can find the max at any time. So, I mean, we just kind of chatted about this one algorithm, but depending on the question that if the input was, if the Skyline was integers as opposed to floats, one algorithm works better than the other. If you're allowed to get away with floats, you can't, I'm sorry, if you're allowed to get away with integers, you'd use one algorithm, which is a lot faster. That algorithm, by the way, the algorithm that does the integer version, how much time would it take? Well, we'd have to write zeros. Let's say the input would actually be a combination of how long the Skyline is and how many buildings there are. So if the Skyline went on for millions and there was only 2 buildings, that algorithm takes a long time. Whereas the algorithm where you just read buildings and non-buildings would just take a shorter number of steps. But it would we would end up writing zeros through all the arrays, through the height array. Then for every building, we possibly increase it to a higher number if we need to. So that algorithm would take however long the city is, and then for each, the thickness of each building could be an additional step. So that one's kind of tough to quantify. It's a combination of how long is the skyline of the city and how many buildings. And sometimes the new building is smaller than the one we had, so we don't have to replace the number, so there's some luck involved. But you kind of get an idea of how much work would be involved in solving that problem. So this is an example where we have a question where you're given input that will give, from a point of view, what a picture would look like. And they actually use algorithms something like this. Now, suppose hypothetically I gave you the height, and then instead of the left and the right, suppose I gave you the left, right, and the thickness of the building. So it would be a 3-dimensional building instead of a 2-dimensional building. You could solve the problem from this point of view, right? We're solving it from this point of view, but you could also, you have enough data to solve it from a side view. Now the question is, a really interesting question is, if the input we could do from this point of view and from this point of view, could you do it on an angle? Yeah. Now, you ever watch football games, the NFL games, where they're showing a play, and then they freeze it, and then it wraps around to the other side of it? They don't have a camera at every angle. They have a camera at some of the angles. And then they start merging. They start doing an algorithm where they have one picture and another picture and say, what would it be like from a combination view?
Do a projection.
Yeah. And if you look at it real close, it's not quite, it starts to look a little animated, then it turns back to a real person. But that's what they're doing. They're taking an algorithm like this one, looking at it from this point of view, a side point of view, and then coming up with an algorithm that does a combination view, and then having them shown really fast. But those are really interesting. That would be a fun job to get. Working for whatever, ESPN or whoever has that camera. But so the thing is like, okay, so what we're going to look at is, we're going to have problems, right? A problem is, here's the scenario, and I want to get from point A to point B. We're going to want to come up with algorithms. Well, it looks like there's many algorithms to solve every problem. We'd like to come up with the best algorithm. And we're going to realize that the best algorithm, some algorithms are better than others, and sometimes certain restrictions cause some algorithms to not work, and then you have to find another algorithm. But we're always looking for the best algorithm. So now what we have to do is we have to come up with a mechanism that says, why is one algorithm better than another algorithm? Like when you're driving in your car, maybe time or gas mileage or something is the way to determine the best algorithm. We have to come up with some mechanism that says, if I have a certain algorithm, how good is it, and is someone else's algorithm better than mine? And mine might be better for n is between 0 and 20, but after that, the other algorithm turns better, and we want to just say one's better than the other. So we'll come up with some kind of mechanism for that.